As part of the present administration's efforts to curtail the spread of coronavirus COVID-19 ravaging the country and the world at large, Edo State Ministry of Education, in collaboration with Edo Broadcasting Service (EBS) and Academic Staff Union of Secondary Schools (Asuss), is organizing a television program for students in senior secondary schools, particularly those writing the West African Senior School Certificate Examination (WASE), the National Examination Council (NECO), and National Business and Technical Examination Board (NAPTEB) for the year 2020 in the months of May, June, and July. The program will be held on EBS television channel every day from 12 noon to 1 p.m. beginning from Monday, April 6, 2020. The subjects selected for these programs are Mondays Mathematics, Tuesdays English Language, Wednesdays Physics, Thursdays Biology, Fridays Geography, Saturdays Civic Education and Economics, and Sunday Chemistry. Parents and guardians are therefore advised to draw the attention of their children or wards to this opportunity during the stay-at-home period.
Good day, our wonderful viewers at home. I am Mr. Eugene Ohide. I'll be your physics tutor for today. And then, as we've been well informed, this program is designed for all secondary school students, particularly for those in our certificate classes, the SS3 students. Now, physics has a very broad curriculum. The syllabus of physics is broad, but we'll make efforts to pick out the salient topics, the most important topics, where these examination body sets or draw their questions from. And among the lot of it, we'll be dealing with motion today. Our topic for today shall be motion. This is an important part of our SSC examination, SSC. Now, when we say motion, is not as common as the name tries to imply. There are more to it than it catches the eye. When we want to look at motion, we examine motion, extract through the meaning of motion, the type of motion. We'll look at some of the concepts used in describing motion. Then, of course, we'll look at the motion graphs, the various graphs that we use when we describe motion. We'll talk about the equation of uniformly accelerated motion. That's the common equations we use in solving problems that has to do with motion, particularly uniformly accelerated motion. Then we'll look at motion under gravity. Then we'll talk about projectile, simple harmonic motion. With this coverage, we must have touched about 20% of the questions that are being asked in an examination in our external exams. Now please, our time may not permit us to pick all, but I think for today we should be able to cover the first four at least today. Let's go straight. What is motion? What is motion? Motion simply describes a body change position, the change of a body's position with time. As I am right now, I can't be said to be on motion because I'm stationary. But by the time I begin to change my position with time, I'm said to be on motion. That's what motion simply talks about. Now, my hands are on motion, even though my entire body is fixed, but these hands are on motion because its position is changing with time. So that's the simple concept of what motion is all about, the change of the body's position with time. Now, what are the types of motion? Many persons, or many scholars have classified motion in different ways, but we shall look at four common or basic types of motion as it relates to our scope. And these are, we have the random motion, oscillatory motion, translational motion, and of course, rotational motion. There is another classification. I'm going to differentiate it from these four. They call it relative motion. I'll go a little on that to tell us the difference between other classifications and that of relative motion. What is random motion? Random motion simply describes the movement of a body in an haphazardical manner. The movement of the body in a zigzag order. For example, the movement of your house flap can be classified as random motion. And one common example that is associated with sciences is the movement of gas particles. They move in zigzag manner. So such motions are classified as random motion. Then we have oscillatory motion. Oscillatory motion is simply the movement of the body to and fro about a fixed point. The movement of the body to and fro about a fixed position. Such a motion is known as an oscillatory motion. Common example is the movement of our child's swing, the one used in school. Then we have another example, the movement of our simple pendular ball. I would like to please get it clear or draw attention to this. When you are asked to state examples of oscillatory motion, you don't state the simple pendulum as an example. No, it is not an example. It's the movement or the motion of a simple pendulum. That's an example of oscillatory motion. Then we have the translational motion. Translational motion simply means the movement of an entire body from one point to another, from one position to another, especially along a straight path. For example, the movement of the student from our class to the laboratory is an example of translational motion. The movement of a vehicle, a car, from Ring Road to Ramat Park is an example of translational motion. But please note it, a body can exhibit more than one type of motion simultaneously. Just like the example I gave to you, the movement of a car. I will get back to that again. Then we have our rotational motion. The movement of the body along a concentric circle. A concentric circle, that means the entire body is moving around a circular path at a fixed axis. For example, the wheel of a car is undergoing rotational motion. That's why I said a body can undergo two types of motion simultaneously. A car driving from Ring Road to Ramat Park is undergoing both translational motion and rotational motion together because the tire is rotating. So we can see these are the various and the common types of motion as it relates to our scope of study. But some persons add this, the relative motion. But relative motion per se, one is described as a type of motion. It is the description of motion. Relative motion has to do with the description of motion with respect to what we call a reference frame. That is, when you want to describe the movement of the body from another point, that is what we call relative motion. So a body does not undergo relative motion. Rather, we talk about the description of the motion of a body with respect to what we call a reference frame. For example, when you are standing by the roadside and a vehicle drives by, the way you judge the speed or the velocity of such a vehicle differs from another person who is in a moving vehicle, either moving in the same direction with that vehicle or in opposite direction. So we are talking about relative motion. I see the velocity different from what the other man sees it. That's what we mean by relative motion. A quick shot on that. When we discuss relative motion, most times we talk about relative velocity. How do we find the relative velocity? That's simple. Relative velocity, please take note. When the both bodies are moving in the opposite direction, to find their relative velocity or the relative velocity of the motion is simply the sum of the individual velocities. For example, a vehicle is moving with 20 meters per second and passes another vehicle in the opposite direction, moving with 80 meters per second, the relative velocity of the motion is 100 meters per second. That is 20 plus 80. Then when they move in the same direction, the relative velocity is the subtraction of the smaller one from the bigger one. I normally use this illustration to help my students pass the message clearly. For example, if I'm in a vehicle and another vehicle is trying to overtake my vehicle side by side, I don't see that vehicle overtaking me moving at a very high speed. I can say hello to somebody who is in the other vehicle, even though that vehicle is moving at a high speed. Just because we are moving in the same direction, I see the velocity to be slow. That's why when they move in the same direction, you subtract one from the other. But when they're moving in the opposite direction, before you say hi, that vehicle has zoomed off. That's why it could help us to know when to add and when to subtract. So the summary of it is, when they are moving in the same direction, to find the relative velocity, you subtract the smaller one from the bigger one. Then when they're moving in opposite direction, to find the relative velocity, you add the both of them. So I believe my students or my viewers must have gotten a better understanding of what random motion is, oscillatory motion is, translational motion, and rotational motion. They understand very well that relative motion is not a motion undergone by a single person, but rather a description of the type of motion. Now let's go forward to talk about some of the concepts used in describing motion. Some common concepts we use in describing motion involve. Okay. We can't talk about motion without a better understanding of these concepts: position, distance, displacement, speed, velocity, and acceleration. Each time we describe motion, this concept comes into play. What is position? Every viewer at home occupies a position right now. Every object around us occupies position. So we can simply describe position as a point in space. Position simply means a point in space. Then when we're not talking about distance, but please, very important, position, a point in space, varies. There are coordinates, what we call, I made reference to, frame of reference. When I want to describe my position, the position of this table from the ball differs from the position of the table to where I am now. So we cannot discuss position without a frame of reference. And one common frame of reference used in describing position in physics and even in mathematics is our Cartesian coordinate system. When we plot our graph, usually we plot our graph, common graph in mathematics and physics, using the x and y coordinate system, where this is my positive y. This is a frame of reference in describing position. So any points I'm going to be picking in space have a corresponding y and x value. We call it the coordinate of the point A, x and y. So every point on this graph, B, C, is occupying a position which can be described by our reference frame, which is the coordinate system. And in that case, we have the value of the x traced down, for point C, whatever I have here as x, and whatever I have here as y, it's going to be a negative value, are the coordinates of this point, which we use to describe position. Okay, that's position. What is distance? Distance simply means the space covered by a body in motion. It simply means the space covered by a body in motion. As I'm moving, I'm covering space. That space connotes distance. That space cover connotes distance. And is measured in meters. We measure it in meters. Now, but please take note. The space between me and the table here is also distance. But not just distance this time around, it's called displacement. That is why most times people interchange distance and displacement. They connote space cover, but the major difference is that while distance talks generally about the size of the space, which we call the magnitude of the space, displacement gives us a sense of direction. Displacement gives us a sense of direction. So when I'm talking about the distance from here to the table, I'm talking about displacement. What is displacement? It means distance in a specified direction. Displacement simply means distance in a specified direction. If I walk up to you and say, I have covered 10 kilometers this morning, I'll just describe distance because there is no sense of direction to what we're discussing. But if I walk up to you and say, I've covered 6 kilometers from Aduawa to Ring Road, I've just talked about displacement because I have specified the direction, Aduawa to Ring Road. So that's the difference between distance and displacement. Displacement is distance in a specified direction. And very importantly, we also need to have this understanding. If I can walk up to this platform, and in the process of teaching you here, I'm covering a lot of distance. I started at that spot. I have walked here, and I'm back here to this position, and back to this position, and probably going back to this position. My distance is the overall sum of the spaces that I've covered. But what is my displacement? My displacement simply means the distance from where I am right now to the current position, the initial position I started with. So, for example, a boy walked 20 meters due west. Thereafter, he walked 4 meters due east. What is his distance and what is his displacement from its original position? Simple. We have our cardinal axis, the north, east and west, at the back of our mind to guide us. So when we say a boy walked 20 meters due west, if the boy is starting from a position, he goes towards this direction. From here, where he's starting, to here, where he is now, we're told is 20 meters due west. Thereafter, he walked 4 meters due east. That means he walked from here, due east, back towards, and this is 4 meters. And the question says, what is his distance and what is his displacement? The distance and the displacement are not the same. The distance is, he moved 20 in the first instance. Thereafter, he moved another 4 meters. That makes it a total of 24 meters. That's the distance. But his displacement, this is where he is currently, and this is where it's starting. So what is the distance between here and here? Of course, that's 20 minus 4. The displacement is therefore 16 meters. So I believe we've gotten a better understanding of what position, distance, and displacement means. Displacement is also measured in meters, just like distance. They share common unit because they pass similar information, but with some differences. One being a vector quantity and the other a scalar quantity. For those of us who have understanding of the definition of vector and scalar, I think classifying them is very easy now. We've said displacement has to do with distance in a specified direction. And when direction is specified, such quantities are called vector quantity. Therefore, displacement is a vector quantity, distance is a scalar quantity. In the same dimension, we have speed and velocity. Two common terms people use interchangeably, but connote different things in detail. We could call them brothers or sisters because one can take identical twin. We could call them identical twin. One can mistakenly be used for the other, but it is important we know that they connote different concepts. What is speed? Speed is the rate of change of distance with time. The time rate of change of distance is what we call speed. For example, everybody in motion has speed. I'm going to walk from here to the end of this point. Then watch me come back. You understand the picture I'm trying to explain. From here to that end is the same distance. But now, I took time to walk to this place. I also took time to walk to this place. But you agree with me that both movements are not, they don't take time, they take the same time. The time differs. I seem to be slower when I was going, but faster when I was coming. So I covered the same distance at different time interval. That's speed. That means I have speed while going. I also have speed while coming. But the two speeds are not what? The same. That's why we are saying speed is the rate of change of distance move with time. And simply, our speed is therefore given by this formula. The distance you move over the time taken. Of course, those running 100-meter race, you agree with me that speeds are not the same, even though we are covering the same distance. They use time. Those who cover the speed, if you look at the distance, speed is a function of distance and time. And what do we mean by speed being a function of distance and time? Speed depends on your distance and your what? Time. The higher the distance you cover in smaller time, the greater your speed. So time is a major function here. It's an inverse proportionality. The longer the time you take to cover such distance, the smaller your speed. So that's speed. Distance moved over the time taken. Please notice, from the formula, we can derive the unit for speed. Distance is measured in meters, symbolizes as m. Small letter. Time is measured in seconds. X. So when we tell you the unit for speed is meter per second, it's just from this definition, which simply means meter per second. The ratio of meter over second. Now, velocity, like I said, the twin sister to speed, is the rate of change of distance in a specified direction with time. If you listen to me carefully, I've added something to it. Velocity is the rate of change of distance in a specified direction with time. In other words, I can say, velocity is the rate of change of displacement, because distance in a specified direction is displacement. So I would say velocity is the rate of change of displacement with time. So you see the picture now. Both velocity and distance connote almost the same thing. The major difference is just that velocity has to do with distance in a specified direction. The distance covered, the rate of change in a specified direction. So, if I walk up to you and I say, I drove 20 meters per second today, I just gave you my speed. I drove 20 meters per second today, I just gave you my speed. But if I tell you I drove 20 meters per second today for Ring Road to Idiot College, I just talked about velocity because the direction has been specified. So that's the major difference between velocity and speed. So they are both measured in meter per second. So velocity on the other hand, abbreviated as well. Displacement over time. And as we know, displacement share the same unit with distance. So it is meter per second. So that's what speed and velocity stand for. Quickly to note, from our description, speed is a scalar quantity, while velocity is a vector quantity. Okay, let's quickly look at the last of the list we have here. Acceleration. Acceleration. What is acceleration? Acceleration simply means the increase. I'm going to differentiate this statement. Please listen to me carefully. It simply means the increase or decrease, the rate of increase or decrease. So otherwise you could say is the rate of change of velocity with time. The rate of change of velocity with time. I'll demonstrate it shortly. Now, I'm walking. If you notice it, at a point in time, I increase my velocity. That means I am accelerating. If I'm walking slowly like this and suddenly have to increase, I have accelerated. At that point in time, I increase my velocity. So acceleration simply means the rate of change of velocity with time. As simple as it is. But most students mistake this, that acceleration is velocity over time. A common question I used to ask students, and I know many of you watching me now will also be misled with your answers. Now, a body moves with a velocity of 20 meters per second for 5 seconds. What is the acceleration? A body moves with a velocity of 20 meters per second in 5 seconds. What is the acceleration? Some of you are responding to me 4 meters per second already. That I know. Some persons are already giving me the answer. It's 4 meters per second. Yeah, I know, but you are wrong. For those with this misconception, they will tell me acceleration, since the velocity is 20, the time is 5. That means 20 over 5, and that will give us 4 meters per second squared. If you do this, you are wrong. The acceleration of that body is 0. The acceleration of that body is 0. Why? The question says, a body moves with a velocity of 20 meters per second in 5 seconds. We were even told that there was a change. The body didn't change its velocity. If there is no change in velocity, acceleration is what? 0. So that question is 0 because there was no change in velocity. Even though there is a velocity and time was involved, doesn't mean that acceleration is 4. So please take note. Acceleration is not just velocity over time per se. It's the change in velocity with time. So very important to note. Acceleration is change in velocity with the time taken. The time taken to which that changes occur. Now, let me differentiate. When I started, I was trying to draw attention to the fact that acceleration could either be an increase in velocity or a decrease in velocity. That's why we have acceleration could either be acceleration or retardation, otherwise known as deceleration. When a body is increasing its velocity, such a body is accelerating. That's positive acceleration. Then when a body is decreasing its velocity, the body is retardating, or what we call deceleration. So the increase in a body's velocity with time is known as acceleration, while the decrease in a body's velocity with time is known as deceleration. So the two concepts should be well taken. Acceleration has to do with increase, deceleration has to do with decrease. Generally, they are all described as acceleration. Either a positive acceleration or a negative acceleration. So please, let's take note of the difference. These are the major concepts we use in describing motion. We talked about position, we talked about distance, we talked about displacement, we talked about speed, velocity, acceleration, stroke, retardation. Quickly, we shall be discussing the graphs, motion graphs. I tagged it motion graph because it's a graph we use in describing motion. The importance of graph in sciences and to the world per se cannot be overemphasized. One of the beauty of graph is that a bulk of information can simply be passed with just a simple representation. That may looking at a representation on the graph, I can describe a series of activities that has taken place. Lots of activities that will be written in thousands of words could just be expressed with a simple graph. That's the beauty of graph. That's why the place of graph cannot be overemphasized when we are dealing with motion. There are basically 3 different graphs we'll be considering in the course of this class or school. And what are they? We have the distance time graph, we have the displacement time graph, and our velocity time graph. We shall look at these 3 shortly. As the name implies, the distance time graph, displacement time graph, and velocity time graph. This simply discuss a plot of your distance against time. Now, common Cartesian plane will plot the distance on the y-axis in meters against our time on the x-axis. That's what it simply means by a distance time graph. Now, very important, because there are several things we could deduce from a distance time graph. When we plot a distance time graph, and we have something like this, a straight line, it connotes something, it sends message. When we plot a distance time graph, and we have a curve of any form, this too sends a different message and gives us a clue of the kind of motion that is involved. When you plot a graph like this, you have what we call a body moving with uniform speed. Uniform speed. A plot of your distance time graph that have a straight line of this format describes a body moving with uniform speed. The question then is, what is uniform speed? What is uniform speed? A body is said to be moving with or a uniform speed, as I'm trying to demonstrate to you now, when the rate of change of distance with time is constant. When the rate of change of distance with time is constant. That means the distance covered by that person per second is always the same. That means a body is moving at the speed of 2 meters per second. 2 meters per second. That's a uniform speed. It talks about that in every second, the body is covering a distance of 2 meters. That's what we mean by a body moving with uniform speed. When you plot such a graph, the distance of such movement against time, it will give you a straight line graph. So that means we can deduce uniform speed. This graph describes a body that is moving with uniform speed. As you can see in the graph, as time runs by, the distance covered increases uniformly. Then, from your graph, we can calculate the value, or what we call the magnitude of the speed. If you take statistic or the data of my movement now, every second the distance I cover, and you choose to plot the graph of the distance against the corresponding time, you can, from your graph, deduce my speed. And how do we deduce the speed from a distance time graph? The speed can be deduced by the slope of the graph. By the what? The slope of the graph. And every student should know how to calculate slope. If I have a straight line graph, to calculate the slope is simply, I'll make a right angle triangle, reasonably large enough, at any point. That's the first thing you do. You make a right angle triangle. Ensure it's right angle. And slope is calculated on my graph. This is my, I'll call it D2, because it's no longer the y-axis, it's my distance axis. And the corresponding time will become T2. While this is my t1 and the distance become d1. Same thing. The slope, which is the speed now, the slope, which is the speed, is equal to the change in the distance axis over the change in the time axis. That will give me d2 minus d1 all over t2 minus t1. Whatever you get in your computation is the speed of such a body. Then we have the second graph. So please, very important to note, for my distance time graph, I could deduce the nature of the motion, whether uniform speed or non-uniform speed. I could deduce the total distance traveled because the latter point here, you trace it to the distance, that gives me the total distance traveled. And the time taken for the motion. Then very importantly, we can deduce the speed from a distance time graph. And we say the speed of a distance time graph is deduced by the slope of the graph. Then very importantly, the non-uniform speed, this is called. A body moving in non-uniform speed means that the body changes its speed, not at the distance covered, not at a constant rate of time. Please observe this. What kind of movement? Your change, the rate at which you cover your distance and time is not the same. Some move with uniform speed, like you could say it's catwalking, walks cautiously, quietly, and at a repeated sequence. But for a non-uniform, you walk fast, you walk slow, your distance, there's no uniformity in your movement. Such kind of movement, when plotted, it will give you a graph of a nation of this kind, or even any zigzag manner. So such a graph will say describe the motion of a body with non-uniform speed, what some would call variable speed. Now, very important to note, you discover that in this our discussion, we are saying no uniform speed, so we don't have a fixed value for the speed. The speed changes with what? Time. On this note, we will talk about what we call instantaneous speed. We'll be dealing with instantaneous speed, which is the speed at a particular instance of time. The speed at any given instance. If we are to add values to this graph, of course we will have probably this is 0, this is 1, 2, 3, 4, 5. For example, we could ask you to find the body speed after 3 seconds. The body speed after 3 seconds is the instantaneous speed, the speed at that given time. And how do we do that? Simply trace that time to the graph. Wherever that time hits the graph, you draw a tangent. Let me illustrate it. If this is a time of considerable t, at this instance, I simply draw a trace it. Wherever it hits the curve, you draw a tangent, which is a straight line from that point. And the slope of this tangent gives you the instantaneous speed at that point in time. I believe my viewers have a better understanding of our the distance time graph, what we can deduce from it. And I've talked about instantaneous speed, which is the speed at any given instance for a non-uniform speed. Good. With this, I won't waste further time on discussing your displacement time graph because it's identical with your distance time graph. The difference is replacing distance with displacement. For displacement time graph, we are no longer plotting distance against time, but rather we are plotting displacement against time. And a smart student should be fast to draw my attention that if we are dealing with displacement against time, this shouldn't be uniform speed anymore. Rather should be uniform velocity. That means, of course, this will also change from non-uniform speed to non-uniform velocity. And I believe If I ask you as a student, the slope of a displacement time graph will be what? Would it be speed? No, it will discuss or describe velocity. So that's the difference. The slope of this graph now talks about what? The velocity of the body, and similarly we're talking about instantaneous velocity. So I won't need to start laying more emphasis on that. The same information for distance time graph is the same for displacement time graph. Just that in distance we are dealing with speed, while in displacement we are dealing with velocity. So that will take care of our distance time graph and our displacement time graph. Let's quickly look at the last graph we have there. Velocity time graph. Velocity time graph. As the name implies, a plot of velocity against the time. Such a graph is known as velocity time graph. I have three of them written here. Figure A, we have figure B, figure C, figure D, figure E. And I believe that a smart student will agree with me. If I am dealing with velocity time graph, just the same way we dealt with displacement time graph, and we are discussing velocity. Displacement time graph, we are discussing velocity. Like a displacement over time is velocity. That means a velocity over time should be what? Acceleration. So in a velocity time graph, we'll be discussing acceleration. I guess all with me. So we have various shapes our velocity time graph could take. In our figure A, for example, it connotes a body that is moving with uniform acceleration. It connotes a body moving with what? Uniform acceleration. As the name implies, please, when you see straight line, they discuss uniformity, something that is constant. So figure A above describes a body moving with uniform acceleration. Please let me quickly say this. When a student is asked, we said before now acceleration is measured in meter per second. If we didn't mention it, note it, acceleration is measured in meter per second square. There's a square. Meter per second square. So I want to ask, if I ask, what does it mean for a body to be moving with a uniform acceleration of 2 meters per second square? Please take note. We've said before now, acceleration talks about the increase in velocity. The increase in velocity. So a body is said to be moving with an acceleration of 2 meters per second square when it increases its velocity by 2 meters per second in every second. Please take note. A body moving with this acceleration means that the body is increasing. To accelerate means you are increasing. It means the body is adding 2 meters per second to its velocity in every second. In the first second, if the velocity was 4, after the first second it becomes what? 6. After the next second it becomes what? 8. That means as the second goes by, it adds 2 meters per second to the value of its velocity. That is what we call uniform acceleration. So a simple definition, a body is said to be moving with uniform acceleration when the rate of change of its velocity is constant. When the rate of change of its velocity is constant, such a body is said to be moving with uniform acceleration. I believe the message is being passed. So in such situations, the graph gives us a straight line graph. Take note, this my graph is starting from the origin, from the rest position. That means the body started accelerating uniformly from rest. If I want to describe a scenario of a body that started with a given velocity, after a time it begins to what? Accelerate. The graph will not start from the origin. We'll have graph connotes a body whose initial velocity was not 0. It has a value, u. When it starts from the origin, that means the body starts from rest. So please take it. Okay, let me quickly run through this so we'll pick some past questions. Now this one connotes uniform acceleration. This one connotes uniform deceleration. If you see the thing is dropping, decelerated and came to rest. Now this one connotes uniform velocity. Please take note. At this point in time, the body was not accelerating. So we have a straight line graph like this, which shows that velocity is not changing. So this is uniform velocity. Acceleration here is 0. Then the other two latter graph, figure D and E, connotes no uniform. We talked about no uniform before. This one is no uniform decreasing acceleration. This is no uniform increasing acceleration. Please take note, in both cases, velocity are changing. But this one, the rate at which the velocity is changing, keep decreasing. You add 5, the next second you are adding 4, the next second you are adding 3. You are accelerating but at a decreasing rate. This one, the rate at which you are accelerating keeps increasing. You added 2, the next second you are adding 3, the next second you are adding 4, and so on and so forth. So this connotes non-uniform decreasing acceleration, and this connotes non-uniform increasing acceleration. Please, let's just quickly take a few fast questions. We have the first one. The time rate of increase in velocity is called, without wasting time, you agree with me that the answer is acceleration. We have A, force, B, momentum, C, acceleration, D, speed. If you've been following us carefully, the answer is directly there, acceleration. Then we have the second one. The area under the velocity time graph, very important please, connotes, as we are discussing, please take note. When we draw a velocity time graph, the area under the figure we are describing is the distance traveled. We talked about the acceleration. So, in this my graph, what figure is this? Is a triangle. So the distance traveled by such a body is the area of this shape. That is the area of the triangle, which will be half breadth times height. Please take note. We can deduce that from our velocity time graph. The area under the graph. If this is the graph I'm considering, the figure here looks like a rectangle, which will be length times breadth. So that will take care of the answer we have there. That the area of the lecture, I think I defined the uniform acceleration to us. Then we have a calculation here, and it reads, as you can see from the screen, a car starts from rest and accelerates uniformly. A car starts from rest and accelerates uniformly for 20 seconds to attain a speed of 25 meters per second. It maintains this speed for 30 seconds before decelerating uniformly to rest. The total time for this journey is 60 seconds. The questions are as follows. Sketch a velocity time graph for the motion. Use the graph to determine the total distance traveled by the car, the deceleration of the car. Let's quickly take it. Very important. Sketch a velocity time graph of velocity against time. Let's interpret the question. A car starts from rest and accelerates uniformly for 20 seconds. That means to have started from rest, your initial velocity was what? 0. So we are starting from the origin. Start from rest, accelerated uniformly. Uniform acceleration connotes a straight line. And it took it 20 seconds. That means the time here is 20. That's the first phase of the motion. We're told, and attain a speed of 25 meters per second. That means the speed, okay, we use speed now. 25 meters per second. That takes care of the value. After 20 seconds, the new speed is what? 25 meters per second. Starting from 0. Now, it went further to read. It maintains to have a straight line like this for another 30 seconds. Please take note. It will be wrong to put 30 here because the time is increasing. The last time was 20. This time now becomes 20 plus 30. That will give us 50. Here becomes 50. And we are told the body decelerated uniformly. That means a straight line down to rest. And the total time for that journey was 60 seconds. That means as at the time it's coming to rest, our time here is 60. My viewers, the first answer, question and the answer, show the velocity time. We've done it already. And as for random, lastly, they said we should calculate two things from the graph. Calculate the distance traveled and the deceleration. I said it when I was teaching. In case I omitted it, please note it. Like you said, the distance traveled is the area of the figure under the graph, while the acceleration or deceleration is the slope of the graph. So let's take the distance quickly. What figure is this? This is a trapezium. So we're going to use the area of the what? Trapezium. Alternatively, we can break it into three figures, which is a right angle, a triangle, a rectangle, and a what? Triangle. Whichever way gives us the what? Answer. So the total distance traveled is simply alpha. Says total distance is equal to area of a trapezium. Mathematically, area of a trapezium is half A plus B times height. Where the length from here to here is my A, the length from here to here is my what? B, and this is my what? Height. So my answer is as good as 1, 2. A becomes, please take note, here to here is 50 minus 20, which is what? 30. Plus 60 minus 0, which is what? 60. And the height, 25. When we solve this, 1 or 2 times 90 times 25. Of course, a quick one. 2 here, 45. So that means our answer becomes 45 times what? 25. We can simply do it somewhere. 5 times 5 is 25. Put down 5, carry 2. 5 times 4. 5 times 5, 25. Put down 5, carry 2. 5 times 4, 20. Plus the 2 carry becomes 22. 2 times 5, 10. Put down 0, carry 1. 2 times 4, 8. Plus that one, 9. That will give us 5, 2, and 11. Which means my total distance covered is 1125 meters, or we could say is 1.125 kilometers, as the case may be, expressed either in meters or in kilometers. And quickly, and lastly, we're asked to calculate the deceleration. If you look at your graph, the body begins to decelerate from this point. This is what connotes the deceleration, this straight line here. So we're going to find the slope of the graph considering this part. And if you look carefully, a right angle triangle has been drawn here already. We will trace this value here to be my S2, and the corresponding end of it here becomes my what? S1. And similarly, if this is my S2, the corresponding value here is my T2, and the correct deceleration. So that will give me deceleration as required is a change in the speed axis. The change in the speed axis, which is my 2 now, S2. 25 minus 0 all over. Please take note. We'll have 50 minus 60. That will give us 25 over minus 10. Automatically, it will give us 2.5 meter per second square. There is a minus sign. The minus sign tells us it is decelerating. So you can see from our question, we've captured more than one velocity time. 1, 2, 3 is showing in the velocity time graph. So for today, I think this is where we'll be running up our classes on motion. I will discuss down to the velocity time graph. Subsequently, we will meet to discuss further. Thank you.